Welcome back, students. Today's lecture is going to be a quick one. We're going to start by finishing up talking about homonuclear diatomic bonds and the last little details we didn't get to last time, and then we'll quickly go over heteronuclear bonds, and it turns out that those are pretty similar. So the learning goals for today are going to be to describe the phenomenon of sp mixing. That's what causes the 3 sigma bonding orbital to be higher or lower than the pi orbitals. We'll review that and we'll talk about why that happens. We'll look at the bond order as is predicted by MO theory and compare that to experimental parameters. And then we'll go through some heteronuclear diatomic atoms. They're a little bit harder, and so we'll just go over them in the ways that they are similar to our homonuclears. So last time we ended with this. We talked about fluorine, we talked about nitrogen, and we filled these diagrams, and filling the diagrams was pretty straightforward. It was just basically following the same rules that we did for atomic spectroscopy in Gen Chem. Now, we noted something interesting, and that was for fluorine, the 3 sigma G bonding orbital here is lower in energy than the 1 pi U. But for nitrogen, the opposite is true. So the 1 pi U was lower in energy than the 3 sigma G. Now, I mentioned that the reason for this had to do with sp mixing. And what that means is that the fluorine orbitals, the s and p orbitals for fluorine, are far enough apart that they are approximately non-interacting. And so we have a bond just between s orbitals and a bond just between the 2p z orbitals. And that's because this energy gap for fluorine is about 21.6 electron volts. So they're too far apart in energy, just like we don't make hybrid orbitals for 1s and 2s orbitals that are even further apart than that. Now, for nitrogen, the nitrogen 2s and 2p orbitals are only about 12.4 electron volts of energy different. That is close enough such that we see significant sp mixing. And what sp mixing does is it suppresses both of these. So these energies, the antibonding and the bonding orbital for the predominantly S character MOs get reduced, and the ones, the bonding and antibonding for the primarily P character get raised. And that is enough that we can overlap this pi orbital here such that we fill in the pi orbitals first. Now, what does this look like? So we had these cartoons back on this slide, and we can actually use Gaussian to get these MOs and see what they look like and see if the cartoons are any good. And for fluorine, we see that our bonding orbital here, so this is the 2 sigma G bonding orbital, it looks predominantly like a bonding orbital made from 1s orbitals. It's like I took 2 circles and I added them together and I got this oval. And in the same way, the 3 sigma G made from the 2pz orbitals look basically like I added 2p orbitals together. So this shows that fluorine is not really having a lot of sp mixing due to the increased energy. Now remember that Gaussian is not making these sorts of assumptions that we are when we talk about this. Gaussian is actually quantum mechanically evaluating the Schrodinger equation and so forth and giving us its best version of what reality is. Now, what happens for nitrogen? So for nitrogen, we see that this doesn't really look too ovally. And this is the result of the sp mixing. So the introduction of the p orbital here in the bonding orbital changes the physical shape of the orbital. And likewise, this doesn't look like strictly 2pz orbitals. It's more spherical on the outside and less on the inside. So we have some combinations here, some interference, some mixing between the s and p orbitals for nitrogen, where we don't really see that for fluorine. Now, of course, in reality, it's not as simple a case of no mixing and yes mixing. However, what happens is that above oxygen, so oxygen, fluorine, and diatomic neon, if we were to construct an MO diagram for that, those energies are so far away that we don't see enough sp mixing to change the way in which we're filling these orbitals. Since we're doing this primarily qualitatively, that's all that we really care about. Now, as we switch over to nitrogen, we see that this crosses the threshold. So for nitrogen, carbon, boron, beryllium, lithium, the 3 sigma G orbital would be higher in energy than the 1 pi U orbital because of mixing. Now, of course, these are not occupied for atoms that are smaller than nitrogen. So it's really only an issue for nitrogen, oxygen, and fluorine. Another interesting prediction that comes out of MO theory can be seen here for oxygen and boron. Based on the way that these atoms fill orbitals, we can see that they have unpaired electrons, which would make them paramagnetic. The rest of these, so lithium, beryllium, carbon, nitrogen, and fluorine, don't have unpaired electrons, so we would expect them to be diamagnetic. And this expectation is in excellent agreement with experimental measurements that show diatomic oxygen and boron have a non-zero magnetic moment, while the remaining diatomic second row elements do. Another thing we can get is if we look at beryllium, beryllium has a bonding orbital and an anti-bonding orbital full, and we would expect that diatomic beryllium not be a stable molecule. Neon's not on here, but we would get the same thing for neon, where we would have every single bonding orbital would be accounted for by an anti-bonding orbital, making diatomic neon unstable. We can look at bond order here by using our MO theory, and simply we have to take the number of bonding electrons minus the number of anti-bonding electrons and divide that by 2. So if we go back one slide, we would see here for lithium, we would predict a bond order of 1, beryllium 0, boron would be, so we have 2, 4, and then 2 antibonding, so it would be 1, carbon would be 2, nitrogen 3, then oxygen 2, fluorine 1. And we can have this nice plot here of bond order. This plot is very linear because this is simply a plot of calculated bond order using MO theory in our MO diagrams, which are very integer based. Now we might want to compare this to something, and one thing to compare to that works remarkably well is bond energy. So how much energy is stored in the bond? How much energy does it take to break the bond? And we can see a remarkable correlation with this. So the strongest bond here of our second row diatomics is nitrogen because it's our triple bond. Our double bonds are lower in energy, our single bonds are lower in energy as well. And then we have these cases over here where we predict no bonding and we see very, very low bond energies because we don't have a bond. There's no stable bond for diatomic helium, beryllium, or neon. Another thing we can look at is bond length. This bond length, of course, will inversely correlate with the bond. And I brought up here the force constant first. Again, the force constant works pretty well. We can see a very similar trend here for force constant. That's, again, how strong the bond is. And we see an inverse trend for the bond length. It's not as smooth, but nitrogen, the triple bond, has the shortest bond length. And things like diatomic neon and beryllium and helium have long bond lengths, again, showing that they're not very stable molecules. They're pretty far apart from each other. Now, how do we apply this to heteronuclear molecules? One of the first things that we will note is that we lose some of the clearness for labels. So our G and U symmetry, we're relying on the fact that our two nuclei were the same. If the two nuclei aren't the same, we can't apply GU symmetry. We also can't clearly label things as bonding and antibonding. In some cases we can, but in some cases there are other orbitals that are like non-bonding, and maybe you remember that term. So sometimes we'll drop the asterisk labels for antibonding as well. If we know an orbital is antibonding, we'll add that in. Now, how can we fill in, how can we construct molecular orbitals? What kind of orbitals overlap to form new molecular orbitals and so forth? And what we have to do is simply follow the same rules that we did for homonuclear diatomics. Now, it's not as straightforward because we can't obviously say, well, the 2pz and the 2pz have the same energy, but we can do these same rules. So the rules that we have are that orbitals need to have a net overlap and similar energy. So we have to have the same sorts of symmetry. That means S with pz and px with px, py with py. And then we have to talk about energy. And this is where it's certainly not obvious to you guys who don't spend a lot of time thinking about this, what the energy of orbitals are. This is, of course, provided by quantum mechanical calculations. So we can look here. These are an estimate of what these energies are from something like Gaussian. And when you draw it in this way, we can notice that the H1s orbital is relatively close in energy to the fluorine 2pz orbital, but not really anywhere near energy of the fluorine 2s orbital. And so what that means is that this H1s orbital is going to be capable of having overlap with the orbital of its similar energy, which in this case would be the 2pz, whereas the 2f orbital, or the 2s orbital, sorry, is kind of not really going to be able to participate. So in this particular diagram, it is lessened a little bit, but in most respects, we could treat this as if it's not interacting at all. The other 2p orbitals of fluorine, of course, have nothing to interact with for hydrogen. So the 2p orbitals for hydrogen would be way off the screen up here. So there's no overlap for them. And so they're simply non-bonding orbitals. And we treat these orbitals, these 1 pi orbitals, and also really this 2 sigma orbital here as non-bonding orbitals, and we just have one orbital between hydrogen and fluorine, one molecular orbital, and that gives us a bond order of 1 for hydrogen and fluorine. And we can see some of these orbitals here. So here we have the predominantly 2s orbital where the electron is almost exclusively localized to fluorine. Here we have the 3 sigma g orbital that's primarily the 2p orbital for fluorine. And here we have one of the non-bonding pi orbitals where the electrons from fluorine just are localized on fluorine. There's nothing for them to interact with on hydrogen. Don't worry too much about trying to come up with one of these for yourself. Just follow the simple rules that we have, and you'll be able to do all right. So on the homework, I'll provide you with an example with provided energy levels so we can more easily determine which ones are going to overlap. But for the most case, right, we use programs like Gaussian to do these things and predict the energies for us. So the energies themselves are more complicated than you want to be aware of. Just know that what happens is we have to have, of course, the same symmetry, the net overlap, and then similar types of energy. Another thing to note is that the more an orbital looks like one atom, the more of its wave function is described by that atomic orbital. So this 2 sigma orbital down here that looks very, very similar in terms of energy to the fluorine 2s orbital, if we were to describe that molecular orbital, its wave function would be almost completely described by the fluorine 2s orbital. And so this might look, if we tried to write out the wave function, it might look something like 90% like fluorine, and then maybe 10% like hydrogen or even less, right? And this would be determined by the coefficients of its wave function, modifying the 2s orbital from fluorine and the 1s orbital from hydrogen. If we are taking up all of this fluorine orbital, talking about the bonding orbital, the rest of the hydrogen atom orbital must go somewhere, and so it would predominantly be in things like the anti-bonding orbital, since we can't remove that density. We have to account for all of the input atomic orbitals when we're making our molecular orbitals. The last thing I'll briefly mention here is the molecular electrostatic potential. So this is a way that we can use programs like Gaussian to predict the charge or where the charge is located on molecules. This is basically a combination of all of the molecular orbitals. And you can see that if we do something like this, this is the prediction from Gaussian, is that we have a dipole moment of 1.93 dBi, and experimental measurements for hydrogen fluoride provide 1.91 dBi. So our calculations are pretty good based on experimental data. The problem is, or the difficulty is, that charge is not a quantum mechanical observable. There's no charge operator that we can apply to determine the charge. So what do? Well, we simply estimate the charge by modeling in a point charge and saying, what kind of forces does it feel? Is it attractive? Is it repulsive at all the points around our model here? And what this gets us in this case is this red, which is a charge buildup around the fluorine, and blue, which is a charge depletion around the hydrogen. And this makes sense. We expect a hydrogen fluoride bond to be extremely polar with the charge localized to the fluorine. So that's it for diatomic molecules. We've successfully described diatomic molecules using MO theory. In the next lecture, we are going to look at applying MO theory to polyatomic molecules, and we won't go into the same level of detail as we did here for diatomic molecules, but we'll do things like look at hybridization and start to compare VSEPR theory with MO theory. So I'll end by the conclusions here. Our conclusions are that we can combine atomic orbitals to form various molecular orbitals. It's essentially what we're doing in molecular orbital theory. When we combine two atomic orbitals, we always make two molecular orbitals. It's the same thing if we were to combine four atomic orbitals, say 2s, 2pz from two atoms, we would make four molecular orbitals. And we end up having bonding orbitals with lower energy and anti-bonding orbitals with higher energy. The things we need to consider to discuss whether atomic orbitals will be capable of forming a molecular orbital is having net overlap and similar energy. We can use MO theory to predict bond order, which is a good predictor of many properties of the bond, as we saw earlier today. And when we have heteronuclear molecules, we have uneven sharing of electrons, and we're familiar with this as well. So the fluorine, more electronegative atom, would hog the electrons. And what that means is that in the orbitals, the bonding orbitals that are occupied, those have more fluorine-like character, and the orbitals that aren't occupied have more hydrogen-like character. So the electrons are more around the fluorine than the hydrogen. And I'll leave off there, and I will see you guys in class.